Hello and welcome to my channel once again. Today I shall work out one problem from Fourier series and let's see what's the problem for today. Here we have the problem: expand fx is equal to x sin x in the interval of 0 x to 2 pi in a Fourier series. This is our problem. Today I shall show you some shortcut method for performing the by parts integration. You have encountered that the integration involved in Fourier series often are very much tedious, so we have to reduce our workload. So let's see if I can help you in reducing your load. So you know that fx can be written as a0 by 2 plus summation of n equal to 1 to infinity, let's put a bracket here, cos nx plus bn sin of nx. We know that is the Euler's formula. Here fx is equal to x of sin x. Now let's find a0, which is given as like this. Here we have the limit here 0, so the limit should be like this. So fx dx, and so we can write which is equal to 0 to 2 pi, as fx is x sin x. Here we are writing this. Now we have to perform the integration. So for that, let's remember that Liet technique, where L is logarithmic functions, I indices, A algebraic function, T is trigonometric function, and E is exponential function. So here we have x, that is algebraic function, followed by one trigonometric function. So let's write D and say write plus minus and I. D is differentiation and I is integration. Now first write x and sin x. A algebra will come first, so I have written it under D, and I, that is trigonometric function, here it will come later, so sin x is there. Now we have to find the derivative of x, and then it would be 0, second derivative. Now we have to perform the integration of sin x, which will be cos x, and again we have to perform the integration of cos x, that is minus cos x, that would produce minus of sin x. Fine. Now to find the integration, we have to multiply x with this one and 1 with this one. So the integration value will be equal to minus x of sin x, first this one, so x of minus cos x, that is, and minus plus sin x. It is our integration. You can meanwhile check whether the integration is correct or not. If you differentiate this thing, what you can get, let's see. So minus of cos x, I am differentiating this to check whether our integration is correct or not. So I am differentiating, and then it will produce ax of sin x, and the differentiation will produce cos x. So you can find that differentiation produce x sin x, which was our fx, and after integration we have got this. So our integration is correct. Fine. So we can write that a0 is equal to 1 by pi. Now we have to use the limit plus sin x. Our limit was 0 to 2 pi, so it would be 1 by pi minus 2 pi cos 2 pi, and other terms will be 0. You can see that here cos sin 2 pi is 0, and if we put 0 here, then 0 times cos 0 will be 0 and sin 0 is 0. So this should be the value, and that would be minus 2, because cos 2 pi is 1 and we have divided minus 2 pi by pi, so it will be minus 2. Fine. Now we have to perform the integration for finding an. We know that an is equal to 0 to 2 pi x of sin x times cos of nx dx. Now we know that 2 of sin x cos of nx can be written as let's check it, sin of n plus x minus sin of n minus x. Let me check. It is equal to sin of nx cos x plus cos of nx sin x minus of sin of nx cos x, and that would be plus sign ultimately cos of nx sin x. Yeah, fine. So it is there, and we can write that 1 by 1 by 2 pi 0 to 2 pi x times sin of n plus 1 x minus sin of n minus 1 x dx. I think I am correct. Now again for finding x sin of n plus 1 x, for finding integration of x sin n minus 1 x dx. So again write d and I plus minus plus, that is x, and our sin function is this 1 0. It would produce, the first integration will produce n plus 1 by x by n plus 1, and the second integration will produce sin of n plus 1 n plus 1 whole square x. So multiply this, and we will find that integration will be equal to minus of x cos of n plus 1 x by n plus 1, and it would be plus of sin n plus 1 x n plus 1 whole square, right? And let's see what it is producing here. So d and I and plus minus plus, so x 1 0, and we have sin of n minus 1 x, so it will produce cos of n minus 1 x by n minus 1, and again the integration will produce this one. So int value is equal to, integration value will produce x of minus x of x n minus 1 x cos this one, and this would be plus sin of n minus 1 x by n minus 1 whole square. Now we will write the value. So an is equal to 1 by pi minus x of cos n plus 1 x by n plus 1 plus sine of n plus 1 x by n plus 1 whole square, and it was minus sign there. So we have to get it. So plus of x of cos of n minus 1 x by n minus 1, and it would be minus of sine n minus 1 times x n minus 1 whole square, 0 to 2 pi. Now you can see that if we use this positive upper limit 2 pi, then we will get the term, and cos n plus 1 2 pi will produce plus 1, and sine of n plus 1 x 2 pi will produce 0. So we can see that this term will be 0. Okay, and this term will be also 0 under for the first upper limit, and under lower limit, that is 0, we will get every term equal to 0. So we have to perform the calculation by this: minus 2 pi cos of n plus 1 2 pi by n plus 1, and plus of 2 pi cos of n minus 1 2 pi by n plus n minus 1 plus 0, because other terms will be 0. So we can write here 1 by pi let's write minus 2 minus n plus 1 plus of n minus 1, that would be minus 2 n square minus 1, and that would be minus n plus 1 plus n plus 1, and sorry, there was half sign, I have forgotten that, so the half sign should be there. So the value should be minus 2 by n square minus 1. So you can see that an is equal to minus 2 by n square minus 1. However, you can see that the an value is not suitable for n equal to 1. So we can write for n not equal to 1, because if we put n equal to 1, then we will get n a1 equal to infinity. That is not happening. So we have to calculate a1 separately. Let me check the results there if I am wrong. Let me once again check the signs. So how did I get this minus sign? It is wrong. So we have to check the signs properly, otherwise we may be in trouble. We will be in trouble. So I did mistake here, I guess. So I wrote that negative sign here. It should not be there. So yeah, n is equal to 2 by n square plus 1. Now we have to find a1 separately. For that we can write this minus 0 to 2 pi x sin x cos x. Dx, and we have to perform the integration here. So if we divide it by 2 pi, then we can write x sin 2x dx. So we again write that di technique, that is x sin of 2x and 1 0, that will produce cos of 2x by 2, and it will give you minus sin of 2x by 4. So equal to 1 by 2 pi minus x cos 2x by 2 plus of sin 2x by 4. Limit is this. So 1 by 2 pi, and here again we are getting minus 2 pi cos of 2 pi by 2, and this term will produce 0 for sin 2 pi, and 0 will be produced by every term if we use this lower limit. So this is the thing, and we can write 2 pi, and that minus 2 pi will come out of the integration, and it is half. So ultimately we are getting minus half. From a1 is equal to minus half. Now we have to find bn. Bn is equal to 1 by pi 0 to 2 pi x sin x sin of nx dx. So we have to find the integration. I think it would be 0. Well, let's try sin x sin nx. We can write that cos of n plus 1x is equal to cos nx cos sin cos x minus of sin nx sin x. If we add one thing like this, so that would be cos of nx cos of x plus sin of nx sin x. What should be that then? Then we can write sorry, this should be minus sign. This should be minus sign, so we can write here cos n minus 1x equal to minus 2 of sin nx sin x. So we can write that minus half of or we can write cos of n minus 1x minus cos n plus 1x, half of this is equal to sin x sin of nx. Again we have to find the integration, we have to calculate the integration. For this, let's separate the integration like this. Now do the things. D I plus minus plus x cos of n minus 1 x 1 0, and that would be sine of n minus 1 x by n minus 1, and it would be minus cos of n minus 1 x by n minus 1 whole square, and here we are getting plus minus z plus x 1 0, and here it is cos of n plus 1 x, that is integration will produce this one, and cos of n plus 1 x by n plus 1 square. So we can write that Bn is equal to ultimately 1 by 2 pi x of sine of n minus 1 x by n minus 1 plus of cos of n minus 1 x by n minus 1 whole square, and then we have to put one minus sign, and it would be x of sine of n plus 1 x by n plus 1, and that would be uh, cos of n plus 1 x by n plus 1 whole square 0 to 2 pi. So we can see that these values, this will be 0 when we are using cos x equal to 2 pi, because sin 2 pi is 0. So we are getting cos n minus 1 2 pi by n minus 1 whole square, and minus cos of n plus 1 2 pi n plus 1 whole square, minus of cos of 0 by n minus 1 whole square, plus of cos of 0 n plus 1 whole square. So basically this is 1 by n minus 1 whole square minus of 1 by n plus 1 whole square. This is 1 by n minus 1 whole square plus 1 by n plus 1 whole square. So we are getting it equal to 0. So therefore Bn is equal to 0. This Bn equal to 0 only for n not equal to 1. So that means we have to find the value of B1, which can be written as 0 to 2 pi x of sin x times sin x dx, that is 1 by pi 0 to 2 pi x of sin square x dx, and we know that cos of 2x is equal to cos square x minus sin square x, that is equal to say 1 minus 2 sin square x, or 2 sin square x is equal to 1 minus cos 2x, or sin square x is equal to half of 1 minus cos of 2x. So we will use this here, and we will get 0 to 2 pi, half is out of this integration. So x 1 minus cos of 2x dx. You have to find the integration. We can split the integration like this. Can give one bracket there, minus 0 to 2 pi x of cos 2x dx. So we can say that 1 by 2 pi, this will produce x square by 2, 0 to 2 pi minus x of cos 2x, and we have to perform that integration again. So let's write differentiation integration x cos 2x, that would be plus minus plus 1 0 sine of 2x by 2, and it will produce sine cos of 2x by 4. So let's write here x of sine 2x by 2 and minus minus plus cos of 2x by 4, and the limit is here 1 by 2 pi, and that would be 4 pi square by 2 minus of it will be 0 for sine 2 pi. So we can write cos of 2 pi, that is 1. We can simply write 1 by 4, and for 0 it will be again 0, but this would be minus 1 by 4. So ultimately we are getting pi. So hence b1 is equal to pi. So we have found that a0 was let me collect the data. A0 was so A0 minus 2, A0 was minus 2, so A0 was minus 2, and A1 was minus half. A1 was minus half, and An for not equal to n not equal to 1 was, let me check again, something by n square minus 1, where it is 2 by n square minus 1, 2 by n square minus 1, n is equal to 2 to infinity, and b1 was pi, because and bn is 0 for n not equal to 1. Hence we can write that x sin x is equal to a0 by 2, that is minus 1, then we can write minus half of cos x plus pi of sin x, and 2 is equal to 2 to infinity 1 by n square minus 1 cos of nx. So let me check the answer from the book here. Let me check the problem's answer. Page number 372, answer where it is. So the answer is minus 1 plus pi sin x, minus 1 plus pi sin x minus half cos x plus of twice summation n equal to 2 to infinity cos nx by n square minus 1. So we have found ultimately the expression. Hope you have understood the calculation, and I have shown you one shortcut method for performing the by parts integration. It is very useful. If you try it, you will find that it will reduce your workload and it will save your precious time also. So I recommend to use this technique for by parts integration. It will be helpful, and hope you have understood the problem. It is a very important problem you can find. It may come in your examination also, so learn it, and I think now you can do it yourself also. Thanks for watching the video, and if you like the video, please make sure that you click the thumbs up sign there, and if you have some queries, please write on the comment section, and share this video with your friends, and obviously do subscribe my channel. Thanks a lot.